Good morning, good afternoon, or good evening, depending on when you're watching this. Some of you are here live, and others are will be watching this later. So, anyway, my name is Steve Vaisey. I am professor of sociology and political science at Duke University. I am also the director of Code Horizons, which is part of Statistical Horizons. I am very pleased to be able to welcome you to this course on multi-level and mixed modeling using Stata. So before we get started, I want to talk about a couple of items of business. If you have questions for me and you are here live, you can raise your hand in the Slack or in the chat. And I will see it with the number of people who are here right now. If you want to just like ask a question, that's probably fine too. Or if you want to, you can also use the chat if you prefer. That's fine. If you are not currently here, if you're not watching this live, and you have a question for me, you can ask the question using the Slack workspace for which you received a link from Statistical Horizons. So that link the Slack link will enable you to join Slack. If you've never used it before, the way we're going to use it is extremely simple. It's just a way for you to be able to essentially ask me questions. So it's really, we're going to use one channel. It's going to be very simple. So you do not want to miss out on that. I know it's an extra step, but generally speaking, there's a lot of good discussion on the Slack outside of the live, performance of the class. So I recommend doing that. So if you're not live, if you're not here right now, the Slack is a good alternative. The other thing the Slack is good for is if you have a question that I would call, and it's not always easy to tell, but if you have a question that's sort of highly idiosyncratic, if you have a question that's like about your data set or about something that's like more specific to you, the Slack is a great way to ask me those questions without having to, have the whole class necessarily listen to a description of your, research situation. So we're going to try and reserve, our time together as being focused primarily on like general interest type questions. So questions about the methods that we're going to talk about, questions about intuition or how things work. And we're going to save questions that are specific to like your specific data set or situation for the Slack. That's one of its main objectives. Okay. So there is one sort of last thing. I understand everybody's situation is different, so I don't want to put like pressure on anybody. But if you want to have your camera on, it's all other things being equal, I prefer that. I mean, and then I can see you. And so I'm not just teaching to my webcam. If you can't do it or you don't want to do it, that's fine. No big deal. Hello. So we'll stick with that. Okay, cool. It also enables me to see like if somebody looks confused, it's easier to see that when I can see their face. All right. So okay, I think with that we're going to get started on the actual course. Now, you in the Google Drive file that or Google Drive folder that you received access to, there is this file which is read this first. Now, in my experience, people don't generally read it first, and so I'm going to go through. I'm not going to actually literally read it out, but I want to point out a few things. This course is taught using Stata. If you want our code, contact Ashley at Statistical Horizons, and she will be able to provide you with the R code. Okay. Hopefully, you have Stata installed. I'm going to use Stata 18. Stata 14 plus will work for most of the things that we're talking about, if not actually literally everything. Here are 4 packages that you will want to install. 2 of them you can install in sort of the normal way through SSC. These other 2 will have to be installed from different places. So you should run that code if you want to make sure that you have the packages you need for the class. The folder that is in the Google Drive, you want to download that to your computer so that you have access to the data sets and things that we are going to use. Now, this part is a little maybe different for you, so I'm going to go through it in a second. The slides that I have made here are, I made them in what's called Quarto, and then they are in HTML format. So essentially, this right here, this slideshow that you're looking at is basically it's a web page. It's like a web page with pages like this. Okay. And so the nice part about this is that it doesn't matter too much here, but the nice part about this is that it enables me to do things like this, like embed the code for the stuff that you're seeing in the slides. So like, oh, how do I get that? You can see the code. So that obviously on a PDF, and as things get more complicated, you can see this. So the nice part about this is you can see what it is that I'm doing, without having to like go to my code, which I'll also show you where that is. But it's a way for you to see the code even when I'm not like sort of foregrounding it. You're like, oh, how did he do that exactly? It's going to show that. Okay, so that's a really, in my view, a pretty big advantage of this format. You can open the slide file. It's called slides.html. You can open it in Google Chrome or whatever. It'll open in anything. And so yeah, so that's the recommended format. Now in the file, there are PDFs, and the PDFs are just PDFs of this. And so you're not going to be able to do the code folding stuff is not going to work. Okay. So you won't be able to see that. So I don't recommend that format, but if you have a attachment to PDF for some reason, then that's fine. If you want to see the code, like all of the code for the slides, there's a file there called slides.qmd. This is, if you can open it with anything. You can open it with a notepad or whatever. So this is like, I opened it with notepad. This is the code for all of the slides. Okay. So just in case you're wondering like how it all got put together. So if you're ever looking for anything that I did, all of it is just plain text. There's no cutting and pasting of anything into slides here. This is all it's all here. So if you want to see anything of the code, it's in the slides.qmd file. And again, your computer is probably not going to know what a QMD file is. Okay. And so you want to just go, you can open it with anything. Text edit if you're in Mac, Notepad if you're on Windows. Anything will open. Okay. So that's just, yeah. Okay. So that's the idea. That was point 5, and then I already asked you to join the Slack. So I think that's everything. Okay. Any logistical questions before we begin? Okay, cool. All right. Okay, so let's get started. We're going to start with the big picture here. And there's a temptation when I talk about this stuff, when you see what's on the next slide, there's going to be a temptation here for you to be like, okay, this is like throat clearing, preliminaries. He's just sort of getting us warmed up. We don't really have to pay that much attention to this. I know all this stuff already. Do not do that. Don't do it. This is the stuff I'm going to show you on the next several slides is going to be absolutely essential for the whole rest of the course. And it's going to look really familiar at first, but I want you to try to approach it with an open mind, because we're going to try to understand this stuff at a different level. Okay. So we're going to talk about variance for a second. Okay. So variance, so like, I learned this my first stats class I ever took. I learned what variance is. And yes, you did. Okay. But we're going to go much more in detail about what variance is and how it works. And the reason we're going to do that is because variance is a super important part of multi-level models. Arguably, it's the most important thing to understand about multi-level models. Okay. So here's the formula for variance. Essentially, this is the main engine of variance here, which is for every observation I, how different is it from the mean? Okay, really simple. For every single so like we have a long long column of numbers, some outcome, some variable, and we say, oh, what's the mean of that? And how is each number different from the mean? And then we square it, and then we add them all up, and then we divide by n-1. So we divide by n-1 because of what's called a finite sample correction. But the basic idea is we want to take the average squared deviation of y. Okay, so that's what the variance is. I mean, we divide by n-1 instead of n for like technical reasons, but in principle, what we're trying to get here is basically the average squared deviation of y. Okay, so what is the variance of the following? If I had a data set that was 1, 2, 3, 4, 5, Like that's my data set. What would the variance of that be? The variance of that would be the average is going to be 3. Okay. So 1 minus 3 squared, 2 minus 3 squared, 3 minus 3 squared, 4 minus 3 squared, 5 minus 3 squared. We're going to add all those up and divide it by 1 over 4 because there's 5 observations. We're going to divide by 1 over 4. So the variance of this is 2.5. Yeah, variance of this is 2.5. So that's a little reminder for you of how variance gets calculated. Now, we're not going to leave it there. All right. What is variance? So the most important part of variance is this part on the right. The other stuff is just about normalizing. The most important part on the right is the sum of squared deviation. So if you've done a lot of work with regression, you know, the idea of a sum of squares should be pretty familiar to you. And that's the engine of regression, is the sum of squares, the sum of squared deviations. Okay. You probably know that already, but what I want you to think about is that this number quantifies the mystery we're trying to solve in a way. It's basically like, hey, some people are high on this and some people are low. You know, like, why is that? I mean, that's basically what we're trying to figure out most of the time when we do a regression. That some people, you know, if we're studying students, some students are doing great, some students aren't doing very well. We're studying patients, some patients are doing great, some patients are not doing very well. We're studying like people's income. You know, some people earn a lot of money, some people don't earn very much money. Like, what the heck's going on? Like so variance is what helps us quantify the mystery. We study things that vary. And so the bigger that is, and obviously we have to think about units, but the bigger it is, the more uncertain we are about the location of any individual observation. If the variance is large, we're very uncertain about where a random person might be. If the variance is small, then we're like, yeah, well, I'm sure the person's between here and here somewhere. Okay, so that's the idea. All right, so in regression, what we do, and you're used to this, in regression, what we do is we calculate residual variance. And residual variance just means, hey, I want to take my x's, I want to make the best guess that I possibly can for y, and I want to see how much better I can do by taking my best guess based on the x's than I do by just guessing the same number for everybody. So if we have to guess the same number for everybody, the number we guess is the mean. You know, if we don't know, you know, anything else about a person, we're just like, well, what's your best guess about this person's height? Well, what's the average height? I literally don't know anything about them. What's your best guess for how tall they are? What's the average? That's what we do. Whereas with regression, we say, hey, look, we can make a prediction for every single person. So we don't just have y bar here anymore. We have y hat sub I. And what does that tell us? This is our best guess for person I. Y hat is an estimate. It's going to be our best guess for person I. And instead of subtracting the mean from every observation, we're going to subtract our prediction from every observation and square that. So where do we get those predictions from? We don't need to worry too much about that right now. Regression is the most common way to get this. So like, again, don't think about multi-level models quite yet. Just think about normal, good old-fashioned OLS regression. The idea is, hey, y hat sub I is just the expected value of y, given that x, whatever x is, it could be multidimensional x, it could be a single x, it doesn't matter, takes on a particular value. So it's like, oh, we're trying to predict how much money a person makes, and we know their gender, and we know how many hours they work, and we know what their occupation is, and we know how much education they have or whatever. That's going to enable us to make a better guess about how much money they make than if we just know, hey, this person has income. Like, how much do you think it is? Well, in that case, it's just the average. If we know a bunch of stuff about the person, we can make a better guess. And that's where y hat sub I comes from. And so once we've made our guesses, we do the same exact thing that we did with variance, which is we calculate what's called a residual variance. Like, what is the variance of what's left over after we make our best guess, the variance of the residuals? And that variance will always be smaller. That variance will always be smaller than the original variance, because we're going to make better guesses for people than just guessing the mean for everyone. They might not be amazing guesses, but they're going to be, if we know something, we're going to make better guesses about the person than just guessing the mean for every single person. Okay, so that's the idea. So we have residual variance and we have sort of original variance. Okay. All right. So you may be familiar with this in under such names as variance, quote unquote, explained by R squared. R squared is simply 1 minus the ratio of these variances. It's like, hey, what was the original variance? How much variance do I have after I add my predictors? 1 minus that is what R squared is. And so if I start, and we'll make up some numbers here. Oh, okay. Zoom decided to update its toolbar. Thank you. Okay. I don't know if that's good. All right. So let's say, it's 100. Let's say the original variance was 100. I mean, it doesn't matter. The original variance is 100. After we do our predictors, the residual variance is 80. Then our R squared is going to be 0.2, 20. Because we've reduced the variance by 20%. And so, people are always better at thinking about math when they think about it as money. So one way you can think about explain variance is like, well, I started the month with this much money, and now I have this much money. What percentage of my money did I spend? 20%. It's exactly the same with variance. Like how much of my variance did I account for? Explained is a strong word, but how much of my variance did I account for by adding my predictors? And so that gives you a sense of what that's like. And so these concepts are really important. The concept of variance are really important because in multi-level models, we're going to have two sources of variance. We're going to have, and so we need to understand variance in order to understand the fact that we have two sources of variance. Okay. All right. Okay. So we want to distinguish in regression in multi-level models in between within variability and between variability. This is a really important distinction. In fact, understanding this is fundamental to everything we're going to do over the course of this class. Okay. So here are two typical situations. Here are two typical multi-level situations. Okay. The first one is what we would think of as the clustered situation. And the idea here is that we have a sample of 10 students each from 30 different classrooms. And so we use different metaphors for this. We might say that the students are nested in classrooms. This is the language people usually use. And I think the reason they use the language of a nest is like, well, it's like a little bird nest. It's like the circle thing, and there's like little eggs in it. You know what I mean? So we have this visual picture of like, oh, we've got little nest and there's eggs in it, and so the eggs are nested in the nest. You know what I mean? So that's the idea. It's a metaphor. So we talk about students being nested in classrooms, and that's the idea. They're contained inside their classrooms. So that would be a common situation. So the idea here is that we have 10 students each from 30 different classrooms. We have 300 observations. And so generally we call the observational level, the sort of most fine-grained level, the egg level, if you will. We call that N sub 1 or N1, which would be the number of observations, the number of units, if you like, at level 1. And so we have 300 observations, and then N2 is going to be 30, which is the number of classrooms. So we have two different N's now. Instead of just having like a number, how many observations do you have? Well, in one sense, we have 300 observations. And in another sense, we have 30 observations. We have 30 classrooms. We have 10 students each. So in one sense, we have 300 observations. In another sense, we have 30 observations. And we're going to see how the different N's will come to play depending on the variable that we're measuring, et cetera. Okay, so that's that. So this is the first context where we see the utility of multi-level models. The second context is in what's called repeated observations or longitudinal data. And so the idea here is that maybe we have 100 college first-year students. We survey them in fall, and then we survey them in spring, and then we survey them in the summer. And here, even though it's like less obviously a visual metaphor, we could talk about these observations, the 3 observations per person, being nested in individuals, meaning like inside. So I'm a person, and inside me are 3 observations. The first observation you took of me, the second observation you took of me, and the third observation you took of me. And even though these sound like very different situations, statistically speaking, these are extremely similar situations. In fact, almost identical situations. Okay, so the idea here is that we can nest observations inside individuals. And so we have 100 people here, but we have 300 observations, and we can think about those 3 observations each as being nested inside those individuals. So those are the 2 typical situations. Now, this class, as per the course description, is going to motivate most of what we do in this class through the lens of the clustered situation. And the reason for that is because the clustered situation is actually a subset of the longitudinal data situation. And so we're going to start with the clustered situation, and we're going to develop almost all of our ideas in the clustered situation. And then at the end, like generally speaking, after I finish the slides, I have a longitudinal demo where we're gonna show how to apply the ideas that we've developed in understanding multi-level models in this context. We're going to talk about how to implement them in the context of a longitudinal data set, so that you won't see too much of that in the slides, because that's essentially like bonus features. So we'll probably do that on day 3. I mean, we'll certainly do it on day 3 of the course, but we're gonna learn things primarily in the clustered setting, because that's going to be the easiest place to develop the ideas. Okay. All right. So clustered data is going to be look like this. So here's a very simple clustered data situation. I have 2 elementary school classrooms, and I have observations of 5 children inside each elementary school classroom. Okay. So on the x-axis is the height of the person, and on the y-axis is just like density, like, just how common is this? Okay. Now, I drew normal distributions over this, but as you can see, these dots are the observations. It's really not a normal distribution, but I superimposed a normal distribution. But the idea here is I have my 5 dots, and this is height in inches. Sorry, Americans still think in inches. I can't help it. This is Ms. Smith's class, and in Ms. Smith's class there are 5 students. One who's 36 inches tall, one who's 37 inches tall, one who's 38 inches tall, one who's 39 inches tall, and one who's 40 inches tall. And one of them happens to be named Alyssa. Okay. Then we have Mr. Jones's class, and in his class we have observations of 5 students, and in his class we have a student who's 46 inches tall, 47 inches tall, 48 inches tall, 49 inches tall, and 50 inches tall. Now, so I drew little normal distributions here just for like visual guides, but clearly this is not in any sense like normally distributed. Okay. All right. So let's not think about statistics for 1 second. Let's just talk like a normal person. And we would say these are things normal people would say. All right. Alyssa is the tallest student in her class. Yeah, Alyssa is the tallest student in her class. All right. So Alyssa is the tallest student in her class. Why? Because she's the tallest student in her class. Okay, that's why we would say that. Now, if someone said that to you, let's say you're sitting there talking to some of the other parents at the school, and somebody says, "Oh, Alyssa's the tallest student in her class," and you said, "Alyssa's not tall," you would have misunderstood what the person was saying. Alyssa, we're not saying Alyssa should be in the NBA. She's not even 4 feet tall. Okay, but she's the tallest student in her class. All right, she's the tallest student in her class. And so the idea is we're making a within group comparison. We're making a within group comparison. We're saying that for a person in Miss Smith's class, Alyssa is tall. She might not be tall like in general, but for a person in Miss Smith's class, she is tall. So this is an important distinction. We're not saying Alyssa is tall. We're saying for somebody in Miss Smith's class, Alyssa is tall. Okay. Another thing we might say is that Mr. Jones's students are taller than Miss Smith's students. This is a between groups difference. So we're talking about the difference between the groups, And so we're talking about 2 different sorts of things here. If someone said Alyssa's the tallest student in her class, and you responded, but Mr. Jones's students are taller than Miss Smith's students, that would be like grammatically, to me, that would signal a misunderstanding. There's no contrast here. It's not a but situation. It's not like oh yes, but it's not but. It's just and. It's like, and, Mr. Jones' students are taller than Mr. Smith's students, and Alyssa's the tallest student in her class. These are 2 different types of information. One of them is a within subjects or within classroom, information, and the other one is a between classroom information. Okay, within classroom and between classroom. And so this is the kind of situation that we encounter with clustered data all the time. And so this little blue one is like, oh, what if we had to draw a normal distribution over these 5 points? This red one is what if we had to draw a normal distribution over these 5 points? And then the dotted one is what if we had to draw a distribution for all 10 observations. So you can see, depending on how you think about it, this is the sort of total, the dotted line that represents the sort of total distribution. If we think about this is the normal distribution, which it clearly is not, but just for fun. And then, this would be the distributions of the groups. And so you can see there's a big difference in means between these two groups. Yeah. So anyway, so that's the clustered data situation. And so we say things, and normal people, you don't have to be a statistician to say things like Alyssa's the tallest student in her class. People do it all the time. All right. So like, that person's pretty smart for a sociologist, for example. That's something you could say. All right. So it's important to get your reference category correct. All right. All right. So repeated measures data. All right. So this is a very similar situation, believe it or not. And so again, we have 3 measures per person. We have two women that we're following over time. One of them is named Cassidy. One of them is named Hannah. We have 3 observations of each. We have the first year of measurement. We have the second year of measurement. We have the third year of measurement. And so we can see here's Cassidy. This is like a CESD sort of depression inventory score on the y-axis. And so we could see something like, hey, year 1, Cassidy says 15. Year 2, she says 12. Year 3, she says 18. So that's her. Those are her 3 depression scores. Hannah's score is, she gives us a 12, then she gives us a 14, and then she gives us a 10. Okay. So what are the kinds of things we can say? We can say Cassidy was more depressed in year 3 than usual. So here's her observation. So when we say something like Cassidy was more depressed in year 3 than usual, what that means is we're comparing her to herself. Okay. So if we said, Hannah was more depressed than usual in year 2, we're not saying anything about Cassidy. We're saying, hey, Hannah was more depressed in year 2 than she normally is. That has nothing to do. We literally don't need Hannah. We could delete Cassidy's data for that. We don't need Cassidy's data to compare Hannah to herself. Okay. So if we said, hey, in year 2, Hannah was more depressed than she usually is, we don't need Cassidy's data to talk about that. Same thing, if we compare Cassidy to herself, Cassidy was more depressed in year 3 than usual. We do not need Hannah's data to make that statement. Okay, so when we're comparing a person to themselves, just like before, when we said Alyssa's the tallest student in her class, we don't need the data from the other class to make that statement. So it's about a within group comparison. Again, this is a within subject comparison in this case. It's a within subject comparison. And if we say, hey, Hannah is typically less depressed than Cassidy. Well, why do we say that? Well, we say that because on average, Hannah's average is what? 12, 12, 14, and 10. So her average is 12. So Hannah's average is 12. And Cassidy is 15, 12, and 18. So her average, I think, would be 15 if I did that correctly. So on average, Cassidy's more depressed than Hannah. But in year 2, Hannah was more depressed than Cassidy on this inventory. And so the idea here is that when we talk about differences between groups, we're talking about, just like we did before, we're talking about differences between the averages of groups. We're saying like, hey, these groups are different on average, or these people are different on average. That means between subjects, there's a certain way of talking about it. And within subjects, there's a certain way of talking about it. And the same principles apply to both. And the thing that characterizes the multi-level model situation is the fact that we have these 2 kinds of variances. We could not do any of this for a data set where we just have one observation per person, and all the draws are independent of each other. So we just have a bunch of kids. We don't know what classrooms they're in. We just have a bunch of kids. Well, we just say, hey, here's a kid in the distribution, but we can't make a contrast between within and between differences. Okay. All right. So how do we quantify? Because within and between variants are going to be super important. We need to quantify. We need a way of quantifying the degree of within and between variance in a set of observations. So for any set of observations. So remember, I want you to think about it. For the classroom data, there were 10 data points, 5 from one classroom, 5 from the other. In the sort of little longitudinal data set that I gave you here, there were 6 observations, 3 observations of Hannah, 3 observations of Cassidy. And so we could think in a vector like this, like a vector, and remember, vectors is a column of numbers. So don't get confused. Or a column of numbers of 10 numbers, or a column of number of 6 numbers. how do we just describe the amount of variance that is between groups as opposed to within groups? That's what we need to do. Okay. So how is the, like, is a lot of the variance within subjects or between subjects? How do we quantify that? Okay, so we're going to talk about how to quantify this. So we're going to use what's called an intra-class correlation, which is an ICC. Another name for this that is, I think, more like a better name. It's not more correct, but I think it's a better name and has come into use more in the past decade or so, is what's called the variance partition coefficient, or VPC. These are the same ideas. Depending on what field you're in, you might see one used more than the other, but the equation is the same. And this variance partition coefficient is the between group variance over the total variance. It's a proportion. It's the amount of between group variance over the total variance. Okay, I told you variance was going to be coming back. So we need to know variance. Okay, and we could write this more formally. And again, conventions will differ between fields, but one very common way of writing this is to say that the variance partitioning coefficient, which we're going to call rho because of its historical association with an intra-class correlation, and people use R for correlations, and rho is a Greek R. Anyway, so we're going to use rho for the intra-class correlation, and it is going to be tau squared, which is the conventional way to write the between group variance, over the between group variance plus the within group variance, and that's the total variance. So we have the between group variance tau squared, we have the within group variance sigma squared. We're going to take tau squared, and we're going to divide it by tau squared plus sigma squared. And hopefully from this expression right here, you can see that this value can take on values between 0 and 1. Because, let's say tau squared was 0 and sigma squared was something, then it's going to be 0. If tau squared is a high number and sigma squared is a very low number, then it's going to approach a 1, and that's the range of values it can take. So it is an intra-class correlation. It is the variance partition coefficient, but the most important thing to understand is that it is a proportion. It is a proportion. What proportion of the variance is at level 2 or between groups? That's what we're doing. Okay. So now we could do this manually using MATA here, or META. I don't know how they pronounce it. If we generalize from Stata, maybe it's META, but that seems wrong in English. But anyway, so we can use META to calculate this. And you're never going to have to do this. So do not worry about my code. I'm just showing you what I did, but you're never going to have to do this. All right. I'm creating, how do I estimate the total variance? Well, there's a function in META called variance, and I can just give it a list of numbers. So here are the heights. Here are the heights of Miss Smith's class. Here are the heights of Mr. Jones's class. I can just give it those numbers and I say, hey, give me the total variance for that. And it's going to save it as this little variable here, total variance. Then I can say, hey, what's the between variance? What's the between variance? Now, if the two groups are the same size, now I want you to really look me in the eyes here and understand you are never going to have to do this yourself. So do not worry about my code. I'm just showing you a little hack. If the two groups are the same size, we can get the between group variance by just simply replacing every observation with the mean of its group. This is not something you're going to need to know in the future. But I'm just explaining this to you so you don't get. So what I did is instead of putting each kid's height in, I put in all the kids in Miss Smith's class got replaced with the average. All the kid in Jones's class got replaced with the average. Okay. And that's going to give me the between variance. And then I can simply just say, hey, what's the between variance divided by the total variance? And I get this number. And that tells me that in my little fake school kid height data, 93% of the variance is between groups. So what does that tell you? It just tells you most of the difference. Like if I have this vector of 10 numbers and somebody says well, how big is the difference between the classrooms? The idea is 93% of the total variance is between groups. So what that tells you is, yeah, sure, in classrooms, some kids are taller than other kids within classrooms, within these two classrooms, but the real action is between classrooms. Almost all the variance is that, like, in this class, the kids are much taller on average than in this class. And and you can see in that picture, the two distributions don't even overlap at all. You know what I mean? So the idea is that this hopefully should correspond, to your intuitions here. 93% of the variance is between groups. Okay. And so there's no magic numbers here. This is just a descriptive statistic. This is just literally a descriptive statistic. There's no cutoffs or anything like that. There's no magic numbers. This is just a way of quantifying what proportion of the variance is between groups. Okay. So that's the one with the heights. If we did this for the depression, we do the exact same trick. We just say, here are, Cassidy's score, here are Hannah's scores, or vice versa, whichever one I said. I think this is Hannah, this is Cassidy. And then I replace them each with their averages. And then I do the same observation. And here you can see 34% of the variance is between subjects. And hopefully that is not too crazy, because you can see, look, the two groups, the two girls are not very different from each other. They overlap, sometimes. And so, like, yeah, they do differ on average, but only 34% of the difference is between subject difference in this case. And so that's the idea. And that's how we calculate it. And so anytime we have a variable that is measured and it was collected in a way where it's nested in another group, and that group is interesting to us. We'll talk more about all those little caveats later, but when that group is sort of interesting to us, like classrooms or countries or things like that, we want to know this variance partitioning coefficient, or this intra-class correlation. We want to know it because it is just an interesting and useful, as you'll see, descriptive statistic. Nothing has been explained here. All we're doing is we're allocating variance to the right home. If you want to think of it this way, we're not explaining anything. We're just saying, like, this much of the variance is between schools. This much of the variance is within schools. This much of the variance is between people. This much of the variance is within people. So we're not explaining anything. We're just telling you where the variance is. It's a descriptive statistic. Just like when you calculate the mean of a variable, that doesn't explain anything. Just like when you calculate the standard deviation of something, that doesn't explain anything. You calculate the interquartile range of something, that doesn't explain anything. It's just useful. The VPC or ICC is useful in exactly the same way. It's just a descriptive statistic that tells you something about the variable. Okay, so now what are we going to do with this information? Okay, what is the point of this information? Well, we want to start thinking about what we can do when we have multi-level data, when we have data that is observed and that has like a level 1 and again, this, don't get too, like, there's nothing metaphysical going on here about like level 1, level 2. It's nothing metaphysical here. It's just like, hey, I collected data from a bunch of people who are in different schools. I got data from a bunch of the kids. I think school stuff is important, so schools are my level 2, kids are my level 1. So don't think too hard about the metaphysics here. Let's just stick let's keep it very concrete for now, and we can make things, we'll talk in more detail about some complexities later on, but for right now we want to keep things very simple. So we're just going to think about like kids in schools, for example. That's the idea. Okay, all right, so how does this matter? Well, we're going to talk about how this matters in practice, and we're going to have the opportunity to practice a thing that's called partial pooling, which is really the foundation of multi-level models. That's what we're going to do here in the next section. And we're going to do this in one dimension at first. That means we're only going to have one variable, probably the outcome variable. We're only going to do this for one variable right now. Then, soon we're going to extend this to 2 dimensions and higher dimensions. But to start, we're going to just do it in one variable. And this is super important to build your intuitions about what's happening, because pooling is the core of multi-level models. All right, pooling is the core of multi-level models. So we have to make sure we really understand what's happening. Otherwise, we're going to make mistakes. Okay. All right, so here is some data we're going to use. This is fake data. I made it up. This is data from 30 fake schools. And I have 30 fake kids inside the 30 fake schools. All right. And so what I did was, so the pretend measurement here is how many hours did you study this week? So these are kids in schools. It was how many hours did you study this week? That's the variable. So I have 900 observations. I have 30 kids each in 30 schools, so 900 observations. I have how many hours each kid told me that they studied. And this is what 30 little normal distributions look like. And so the idea here is like, here's the distribution for school 1. The next is the distribution for school 2. The next is the distribution for school 3. The next is the distribution for school 4. And if you want to see the code for this, I don't know why I didn't put the code for this in the slide, but the code for this is in the file. All the fake data set's also inside the folder I gave you. But the idea is that it's there. So I have 30 schools, and each one of these little normal distributions is like the normal distribution that I used for every school. Okay, so school 1, and I made it very convenient. They go from left to right. School 1 is the least studious. School 30 is the most studious, and they just go from left to right. Okay, so I made up some fake data so we can illustrate some of these concepts. All right. So let's do some descriptive statistics of my fake data. All right. So this stuff is stuff you already know how it works. Okay, this stuff is you already should know how this works. So this is, hey, what's the average? The average is 9. The mean is 9. How many observations do I have? 900. Do you care about other stuff here? You can if you want. Like what's the smallest value in the data set is 2.02 hours is the lowest amount of studying. About 16 hours is the highest amount of studying observed in the data set. 9 is the median also. About half the data is between 7.5 and 10.5. If you want to do our little friend here, the interquartile range. The standard deviation is 2.29, 2.3. And then, of course, this is the variance. The variance is 5.27, basically. So the variance is about 5.27. That is the total variance of these 900 observations. So remember, these 900 observations vary. Like the least studious kid studied 2 hours last week. The most studious kid studied 16 hours that week. An average kid studies 9 hours per week. And so the total variance is 5.27. And remember what that number means. That is the average squared deviation from the mean. And that's the average squared deviation from the mean. All right. So that's the variance. Now, variances are very difficult to interpret alone because they're in squared units of the outcome. So that's why the standard deviation was, I don't know if you want to call it invented, but defined, is because the standard deviation is in hours. The variance is in squared hours. So it's a little harder to think in squared hours, which is why we take the square root of it for the standard deviation. But all the math requires the variance. So that's why we work with the variance, even though the standard deviation is a little bit harder to understand, or is a little bit easier to understand. So I'll just give you, since we're here and talking about this, I'm going to give you a brief refresher on this, because this is going to come back later. A brief refresher on this thing called the empirical rule, in case you don't remember that. But okay, so here's a normal distribution. I draw with my mouse, and my drawings are not always great, so bear with. Okay, so the idea here is 9 is the average. Okay, 9 is the average. And so a standard deviation is about 2.3. And so what does that mean? That means that about here, one standard deviation out is 11.3. So it's plus 1 standard deviation. It's going to be 9 plus 2.3 is about 11.3. If we go standard deviation the other way, it's going to be, what would that be, about 6.7. Doing a little bit of rounding here. If we go out another standard deviation, we're going to get to about, what would that be, 13.6. Sorry for my writing here, 13.6. And this is going to be, what, 4.4. And so you can see here that this is just a way, if you don't have the full data set, if you have a mean and a standard deviation and something is normally distributed, we have this little trick called the empirical rule that just helps us mentally sketch out what the distribution probably looks like. We just have the mean and standard deviation. And so the reason this is called the empirical rule is that if it's actually normally distributed in practice, what it's going to look like is about 68% of the data is in between plus or minus 1 standard deviation. So but in this zone right here is about 68% of the data. About 68% of the data points is between plus or minus 1 standard deviation. And if we add the outside, if we add the up to 2 standard deviations, the red and the green together is about 95% of the data. Okay, so that's what's called the empirical rule. So if you ever like have a mean and standard deviation and you just kind of want to like do a mental sketch of the of like what the actual full distribution looks like, the empirical rule is really useful, and we're going to use this later when we talk about random slopes. So this isn't just like a fun fact. We actually are going to use this later. So if it's been a while since you've learned this, or you've never learned it somehow, I don't know. Yeah. So then it's just, that's the idea. So that's what the standard deviation is good for, mainly is to sort of mentally sketch this out. But for the math of multi-level models and variance partitioning and things like that, unfortunately, we're going to have to use the variance. Because that's how the math works. But anyway, that's something to be aware of right now. Okay. All right. Okay. So now we can decompose the variance into two variances here. Now, again, you are not going to have to do this. You are not going to have to do this. But Stata has this one-way ANOVA command called one-way that we're going to use for this. And this is the only time we're going to use this ever. Okay, it's the only time we're going to use this. And the reason I'm using it is just for a calculator. I'm using it as a calculator. So I'm using it to do what I did in MATA before, which is just to like calculate what is the between group variance, what is the total variance. That's all I'm using it for. Okay, so when I use it, this might be more trouble than it's worth, in the sense that, I don't want to confuse anybody here. So I'm just using one way as a calculator. We're never going to use this again. So I'm just using it as a calculator. It just does what I want it to do. And so it's going to give us this thing called it's going to give us this stuff called this is the between group variance, and this is the within group variance. Okay. So this is the between group variance, and that's the within group variance. And so actually we have to take that's the sum of squares. So we have to use the information from this. So we're going to take the MSS, which is the between group one, and we're going to divide it by the total of both. Yeah, so it's not exactly that, actually. We're going to divide it by the total of both, and then we're going to get about 0.2. And what does that tell us? That tells us that 20% of the variance is 20% of the variance is at the school level. Okay, so 20% of the variance is at the school level. Again, you are never going to have to do this. I'm just doing this to show you. This is just I use one way as a calculator. I probably am going to regret it, because people are going to think too much about it. But it's just, I promise, it's just a calculator. It's just a way to do arithmetic. Okay, it's just a way to use arithmetic. Okay. All right. So 20% of the variance is at the school level. So what does that mean? That means like we got 900 kids. Some study a lot, some study a little. If we know what school they're in, that's going to help us reduce our uncertainty about where a particular kid is by 20%. So if you want to think about this, as like, I'm afraid of this because I don't want anyone to think it's explanatory, because it's not. So I just want you to think about it informationally. I want you to think about it informationally. Like, okay, I know I'm going to pick a kid at random from this data set. I'm going to pick a kid at random from this data set. And I want you to guess how much that kid works, how much that kid studies. If you're trying to like win the game, you're going to guess 9 pretty much every time. And you're going to like, your guesses are going to be wrong. Like, oh, shoot, this kid's actually 11 and a half, or shoot, this kid's actually 7, or whatever. You're going to get it wrong. All right. But if I tell you like, okay, I'm going to pick a kid from a school, and I'm going to tell you what the average is in that school, and I want you to guess. Well, if you guess the average for that school instead of the average for everybody, you would improve your guesses by 20%. The variance of your guesses would be improved by 20%. So that's the idea. That's the whole idea, is that basically you're going to get it wrong. Your squared deviation, your squared error is going to be 20% better if you know what school the kid came from. That's what this means. Okay, if you want an intuition for what that means. Okay, so it means we do better. We wouldn't get it perfect, but it would be better. Okay, so that's what that variance means. Okay, now here is where we start to get the first thing that is like properly like a multi-level model. Okay. All right. What if we added 2 new schools that didn't have much data to them? So let's say we ran out of money. We doing our giant project on how much kids work in school, and we wanted 30 kids for every school, but for some reason that has nothing to do with anything. We just ran out of money at the end, and we have two last schools, school 31 and school 32. We only have 2 observations each. Instead of having 30, which is what we wanted, we only have 2 observations, 2 kids from each of those 2 schools. So we have 2 kids in school 31, and we have 2 kids in school 32. All right. In school 31, the 2 kids tell us, hey, one of them says, I worked 2 hours. I studied 2 hours last week. And then another kid tells us I studied 4 hours this week. In school 32, the first kid tells us I studied 14 hours this week. And the second kid tells us I studied 16 hours this week. And somebody says to you, I want you to make the best guess you possibly can of the actual average amount of studying that's going on in school 32. I want you to tell me what you think the actual population amount of studying is in school 32. What's the actual average? Now, your first guess might be, well, what's the average of 14 and 16? Well, it's I'm going to guess 15 because that's the average. I'm not going to be very certain about it, so it could be way lower than 15. It could be way higher than 15. Who knows? My confidence interval is going to be giant because I only have 2 observations, but that's my best guess. But then there's something nagging you in the back of your mind. There's something nagging you in the back of your mind, which is that I have data from 900 kids from 30 schools, and the highest amount of studying is 16 hours in the whole data set. And that seems high. That's your intuition. It's like, this seems like a high number. And then you recall that confidence intervals are symmetrical. So you're like, well, my best guess is like 15, but it could be way higher than 15, or it could be way lower than 15. And then you're like, wait a minute. Is it probably like way higher than 15? Like, that doesn't seem right. Like, how could it be way higher than 15? Like, look at all these other schools I got. Like 15 already would be super high for like an average for a whole school, let alone like higher than 15. Anyway, so these intuitions start to fight with you in your brain. And you're like, how can I use this information? Like, at one level, I've just got, 32. I've got, school 32. I've got only 2 kids. I'm trying to make a guess about school 32. What the heck am I supposed to do here? Okay. So there are 3 ways we can make a decision about this. There are 3 ways that we can make a guess about school 32. Okay. The first is called no pooling. And we'll talk about what that means in a minute. The second is called partial pooling. The third one is slightly ridiculous in this context, but it's called complete pooling. It's not ridiculous in general. We're going to come back to it. So we'll say a little bit of a complete pooling. But the main things that we're going to want to talk about right now are no pooling and partial pooling. Okay, those are the main things that we're going to want to talk about. Those are the 3 options. Okay. So if we decide to estimate school 32's average without pooling, so let's talk about no pooling, which is what you've been doing your whole life. If we decide to estimate school 32's average without pooling, that means we cannot consider any other information except data from school 32. Okay, so if we say no pooling, all that means is that you are disallowed from considering any information from any other school. So if I ask you, what is school 32's average amount of studying? You have only one choice, which is to make the guess of 15 hours and say it could be a lot higher than 15. It could be a lot lower than 15. I don't know. I've only got 2 data points, but 15 is my best guess. That's what no pooling is. So this is like obviously super easy to do. That's obviously super easy to do. But our intuitions tell us this is weird. There's something weird here. Our intuitions tell us something's very off. But that's what we would have to do. That's what no pooling is. So no pooling is super easy. Okay. Now we're going to do the hard thing. The next one's called partial pooling. Okay, partial pooling means that we're going to combine cluster-specific data. So remember, we have 2 new schools. One of them has a base of sort of estimated mean of 3. One of them has an estimated mean of 15. We're going to combine that cluster-specific data, the data about the new schools, with data about the distribution of clusters. That means the distribution of schools means has itself a mean. So we can calculate what's called a mean of means. So we could calculate the mean of means for the schools. So we could collapse it down and say, okay, well, the average school has a mean of 9 and the standard deviation of the school means is 1.09. So we could collapse the data set down. So instead of having 900 observations or 904 observations, we have 32 observations, which is just the average for every school. So we have the average of every school. And that tells us that the average school has a mean of 9 and that the mean of means has a standard deviation of 1.09. So that means like, hey, some schools are a little higher than 9, some schools are a little lower than 9, but that's just a way of describing it. Okay. And what we're going to do is we're going to combine this information with this information. So we're going to combine this, and I'm going to give you more detail on this than you could possibly ever want. And the reason I'm going to do that is because I want you to really, in your bones, understand the process that's occurring here, because this is the engine of multi-level models. This is what makes multi-level models. Multi-level models is partial pooling. So we have to understand this. Okay. So this sometimes, this thing that I'm doing here, and I'm going to show you how we do it, but this thing about combining cluster-specific data with data about the distribution of clusters is sometimes called an empirical Bayes estimate. So you may have seen this in Stata. There are estimates called empirical Bayes estimators. And the reason that is, and if you're familiar with Bayesian statistics even a little bit, you know that there's a thing called a prior, and that we're going to take this thing called a prior, and then that comes before the data. Then we're going to look at the actual data, and we're going to combine information about the data and information about the prior to come up with the posterior, which is basically our best guess. Now, in empirical Bayes, what that means is we get the prior, we use the data twice. We use the data to get a prior about level 2, and then we use the specific information from each level 2 unit as the data. So essentially, we're using each data point twice, once to develop the prior, the empirical prior, and then the second to integrate information about the new cluster. So that's why these are called empirical Bayes estimates. So you will see that language in Stata output sometimes. Okay, so what we're going to do is we're going to combine the entire distribution, meaning this whole distribution of schools. You know, the school distribution itself has a mean of 9 and a standard deviation of 1. We're going to use that entire distribution with the specific data from a single cluster to estimate what's called a posterior estimate of that cluster's true mean. And there's nothing like particularly Bayesian about this, despite the language of empirical Bayes. Partial pooling is more general than Bayesian statistics. And so what this does in practice is it shrinks the simple value toward the mean of all clusters. And so we're again, this might not make any sense to you right now. I'm going to show you exactly how this works. So this is just an overview of the process. So partial pooling causes what's called shrinkage, which means pulling estimates that are like outlier estimates in toward the mean. And I'll show you what that looks like. Okay, so here are some things we're going to need to use to calculate the formulas. And this is like, your brain is probably at high risk of shutting off when you look at this. You'd be like, just tell me what this means. Okay, I'm going to. We're going to go through it very slowly. But I really want you to understand, you are capable of understanding this, I promise. This is not some like big derivation, and I'm just going to hand wave a bunch of stuff, and you're going to nod, and we're just going to move along and pretend it didn't happen. Like, I really want you to understand this. So we're going to go through it step by step. It's actually not that crazy. It looks crazy because there's Greek letters and stuff, but it's not. I promise it's not that crazy. Okay. All right. So this is just what we want. Okay. So let's unpack what all these little tiny squiggles mean. Mu hat means the estimated mean. That's all it means. The estimated mean of school J. And then again, school J would mean there's a school 1, there's a school 2, there's a school 3, there's a school all the way up to 32. So what we want to know here is we want to know, like, what is our estimate of each school's mean using partial pooling. That's all that means. So it means, like, this is just what we want to know. What is our best guess about? So if we have J be school 32, which is what we care about. If we want to know, mu hat sub 32, superscript PP just means, hey, what's our best guess about what the actual mean is of school 32? That's the partial pooling estimate of the mean of cluster J. So that's what we want to know. So this is the thing we're actually trying to do. This is the thing we're actually trying to get. Okay, so what are the ingredients? So everything else here is just ingredients to get that. So this is the cake we want to bake. All the rest of the stuff's the ingredients. Okay, so this is the cake. These are the ingredients. So let's talk about what the ingredients are and how we fit them together. Okay, so this mu hat sub J superscript ML, don't get confused by this language of maximum likelihood. The way people talk about maximum likelihood just is so confusing to most people. Literally all it means here is the average. So so mu hat sub J ML for school 32 is 15. It just means what's the average of the data points. That's it. So 14 and 16, we take the average, that's 15. That's it. That's all it means. Okay. We're not going to have time to talk about this, but the maximum likelihood does not mean probably what you think it means. But anyway, it's fine. So it just means a simple mean, yeah. All right, so that's one ingredient.
Sorry.
Yeah, go ahead.
It's Brian. I came late.
Yeah.
I got my times mixed up. Anyway.
Okay.
Is the reason we're doing this is because the two schools, they have very low sample size. We just want to limit their effect on the rest of our estimate.
It's actually not just that. It's that we want to weigh them proportionate. So, like, they do have less weight. So we don't want to give them too much weight, but we want to actually give them the proper amount of weight. And we want to be able to estimate for that cluster what the average amount is. Meaning we want to be able to know for that cluster, like, what is our best guess? So, like, one way to think about this is basically someone comes to you and says, I want you to guess what the average is of school 32. And if you get it right within plus or minus 1 hour, I'm going to give you $1 million. You know what I mean? The question is, what is the best guess? Like, how do you come up with the best guess? Okay. And so, like, something about your intuition tells you that 15, even though it's really easy to get, is not the best guess because it's, like, so much higher compared to the other schools. And so what we're trying to do here is I'm going to teach you a procedure to make the best guess that you can given the information that you have. And it is not just 14 plus 16 divided by 2. I mean, so in one sense, you're right. That it's, we don't want to, like, overweight, observations that might be extreme, but it's mainly because we want to actually make the best guess we can for that school. Okay. So, this mu hat here is the mean of means. So mu we usually use for mean, hat we usually use for mean. So mean of means, the mean of means for all the clusters. And so remember, the mean of means for all the schools is 9. Like, the average school is 9. So the average kid is 9 hours. The average school is also 9 hours. That's just the way I construct it. So the average school has an average studying amount of 9 hours. Okay, so this first two things are pretty easy. Tau squared is the between group variance. I'll show you how to calculate that in this particular case again in a minute. Sigma squared is the within group variance, and remember, like we talked about earlier, the between group variance and the within group variance sums to the total variance. So sigma squared is just going to be the total variance minus tau squared. These will both sum to the total variance. And so I realize this is the most opaque part of this, and we will talk about how to get that in a minute. Okay. N sub J is just how many respondents are in cluster J. So in school 32, n sub j and n sub 32 is equal to 2. We have two kids who told us we have two kids that told us how much they study. So the n sub j in cluster 32 or n sub 32 is equal to 2 here. So this is not complicated. Okay, and then you'll see this r hat sub j is, we're going to use all this stuff to calculate r hat sub j, and that's going to be like an important parameter. That's going to be almost the most important thing in calculating this final thing. So this is what's called a shrinkage factor. R hat sub j is called a shrinkage factor. It's always going to be somewhere between 0 and 1. I think it has a terrible name. What it really should be called, and you should never call it this in print because it's a stupid thing, but for me, it's an easy way to remember. I think of it as a keepage factor, not so much a shrinkage factor. It's basically how much of the apparent weirdness of that cluster do you get to keep? And I'll show you what that means in a second. So essentially, it's like how much of the apparent weirdness of a cluster are we allowed to take seriously? So as r hat sub j goes up, we're like, hey, 15 seems weird, but we should take it seriously. And as r hat sub j goes down to 0, we're like, we think we just got a fluke here. So I'll show you what that means in a second. Okay, so here, let's put all the pieces together. So this is the formula. The formula here is we want to get this. We're going to take the difference between our maximum likelihood estimate, which in our case is 15, minus the mean of means, which is 9. And so the difference between these two is 6. Oops. The difference between these two is 6. 15 minus 9 is 6. And then we're going to add the mean back on. And then this is going to get, so I need to see, this is going to be, that's what we're going to get. Okay. So the idea is we're going to say, hey, look, school 32 seems like it's 6 above the average. How much of that should we keep? Remember, 15 is 6 above the mean of means. 15 is 6 above the mean of means. So the idea here is that, hey, it looks like this is 6. So how much of that should I take seriously? So you can imagine, so you can see really quickly that if r sub j, if r32, and I should probably make that very clear. It's not even r hat sub j here. It's just r. Whoops. It's literally just, r32. Whatever r32 is, when we multiply by 6, that's how much is going to get added to 9, and that's going to tell us what our best guess is, okay? So if r32 is 1, that means our best guess is 15. If r32 is 0, that means our best guess would be 9. Okay, so don't worry about what r means right now. I want you to convince yourself that given this formula, if r was 1, then the answer would be 15. If r was 0, the answer would be 9. Because it's just going to get multiplied. Whatever r is going to get multiplied with the difference between that cluster estimate and the mean of means. Okay, so now where does r come from? Here's the formula for r. The formula for r here, r hat sub j, is tau squared, which is the between group variance, over tau squared, again the between group variance, plus sigma squared divided by the sample size of that cluster. Okay, so I know this is a lot. So this bit here hopefully looks somewhat familiar. This is the exact formula for the intraclass correlation. This is the formula for the intraclass correlation. Okay, except for we're going to, instead of just adding this in, we're going to divide this by the sample size. Okay, so let's see how this behaves. Let's see how this behaves. Oops. Okay, so we're doing the math again. This is all the stuff I showed you. All that's missing is the shrinkage factor. Whatever we're going to get here is going to be multiplied by 6 and then added back onto 9. Okay, so how do we calculate it? Well, we're going to need the total stuff. We're going to need the total variance and the between variance. I'm just going to give these to you, and then we will talk about where we get these later. You remember that we saw the variance of the total data set is actually 5.41. I showed you the original variance, which was like 5.27. That was before I added school 31 and 32 in it. So the total variance is a little bit bigger. It's 5.41. And the total variance of the new data set, this is the variance of the data set of means, is 1.21. Why is that? Because remember, the standard deviation was 1.09. If we square that, it's 1.21. So all it is just, hey, here's the total variance. Here's the total variance of all my 904 observations. So I have 904 numbers in a spreadsheet. I say, what's the variance of this number? It's 5.41. Then I collapse that down to 32 numbers, and that's the average for each, just the simple average for each school. That has an average. That has an average of 9 and a variance of 1.21. So that's where that comes from. So this is the variance of the collapsed data set of means. This is the variance of the original data set. All I do is plug those numbers in, and I want to get R32. So I say, hey, I put, this is tau squared over tau squared plus sigma squared divided by 2. Okay, so it's going to be 1.21 divided by whatever this is, 3.12 or whatever. And that's going to give us 0.365. So what does that tell us? What that tells us is that the best guess of the amount of studying that's actually taking place in school 32 is 11.2 hours. I want you to let that sink in for a second. That is telling us that if somebody, again, said, hey, I want you to make the best guess you can about the school, and if you get it right, or plus or minus 1, if you get it close, I'm going to give you $1 million. Your best actual guess would be 11.2. And I want you to think for a second about kind of how weird that is. Because we have 2 kids from the school. One kid told us 14 hours. One kid told us 16 hours. And our best guess is 11.2. But this is, I assure you, the actually best guess. And the reason that is because we have a bunch of other schools. And so even though we don't have other data from school 32, we know it's a school, and we know a lot about schools because we have 31 other schools. And we know that numbers like that don't really happen very often. So we're like, hey, look, if I collected 2 pieces of data from school 32 and they're high, I believe school 32 is high. I believe it actually, it's a more studious school than average. But am I willing to conclude that it's literally the most studious school in the whole sample based on those 2 people? No. So how do I combine those 2 pieces of information with all the other information I have is this way. And so this process right here of generating this number, which is the shrinkage estimate, this is called the shrinkage factor, but I don't like that term because the higher it is, the less shrinkage is actually going on. So I like to think of it mentally. I never write this anywhere, but the way I think about it mentally is like a keepage factor. Like how much of the apparent weirdness of an outlying observation do you get to keep? So like in this case, here's a school, it's like 6 above the mean. How much of that do I actually get to keep? Well, you get to keep 36.5% of it. You get to keep 36.5% of it. And that's what gives us that estimate of 11.2. So why does this happen this way? All right, so why? If our 32 schools are a sample, if we think about our 32 schools as a sample, meaning that like school 32 is of the same kind of thing as the other 31 schools. Like they're schools. So when we learn something about schools, we learn something about schools. You know what I mean? That's literally all it is, okay? If our 32 schools are a sample, then we can use the distribution of school means to assess the plausibility of any particular school-specific estimate. Basically, what it allows us to do is say, like, this is weird or this is normal. Okay? Like, it allows us to say, this is weird or this is normal. Yeah, it is Bayesian. Like, Courtney, you're right. It is Bayesian, but it's what's called empirical Bayesian. Because we learned about schools from our sample, and then we're assessing each individual school in light of the whole sample. So if you want to think about it, every school's data is doing 2 jobs. It's first basically saying, like, here's what schools look like. And we're saying, okay, let's use all the data to tell us, like, here's what schools look like. And then we're saying, okay, now let's look at each school individually. Given what we know about what schools look like, how weird is this particular school, even though that particular school was used to tell us what schools look like in the first place? So each data point gets used twice, once to tell us kind of what's normal, and then the second time to be evaluated by what's normal. And so that's the idea. Okay. And so so in that sense, it is Bayesian, but it's empirical Bayesian, which is the reason why that term exists. Okay. And so basically what it does is it just allows us to tell us how weird something is. Now you can think about this. Now, one way to think about this is like, I might have a slide on this later, but I'll say it now, is one way to think about this is like, we develop these intuitions actually all the time, like in the domain of sports. Like, let's say, like, like you're watching the World Cup and you see a player from a country you've never seen before, and they're going to take a penalty kick. It's a soccer game. They're going to take a penalty kick, and that basically, like, people score 75%. Like, on average, people score about 75% of penalty kicks. So very high value chance. So if someone tells you in advance, like, okay, I want you to tell me, like, this person's about to take a penalty kick. Well, how do you think, like, what do you think the probability is that this person's going to score a penalty kick? And you're like, well, I guess 75%. And they go and they take it and they score the penalty kick. Then I ask you again, I say, okay, what do you think this person's, like, average lifetime penalty kicks are going to be from now on? Like, this person's going to have an opportunity to take 25, 30, 50 more penalty kicks for the rest of their life. What is the probability? Like, how many of them do you think they're going to score? Now, if you thought about it like the normal way, you'd be like, well, I have one data point. I saw them score. They're 1 divided by 1 equals 100%. My best guess is that they're going to score 100% of their penalty kicks because I have one data point. I saw them score once. They're going to score 100% of the time. I'm not very confident about that, but my best guess is 100%. What empirical Bayes does is says, hey, look, people who are really, really, really good at this score 90% of their penalty kicks. Okay? People are really good at it score 90% of their penalty kicks. People who are really not good at it score about 60% of their penalty kicks. So if I see a person take one and score one, I don't think they're the best ever now. What I think is they're probably a little bit above average. And if I see them score another one, maybe they're a little bit above average. And if I see them score another one, I'm willing to update my view about a cluster. In this case, it's a person, the more information I see. But I don't just, like, say 1 divided by 1 equals 100%, and that's my best guess. So we do this kind of stuff all the time. We do this kind of stuff like all the time. Like, you meet a new person, for example. If you meet a new person and they're a little bit rude to you, generally speaking, you don't think this person's just rude in every single setting. Because you're like, it's very rare for a person to just be rude in every single setting. So, like, you're saying, well, maybe they're a little more rude than usual. Like, a typical person's rude this amount of the time. Maybe this person's a little more rude than usual. But you're not going to, like, have one interaction with someone and be like, they were rude, therefore I'm going to decree that they're rude to everyone. They're rude to their siblings. They're rude to their parents. They're rude to every customer. They're rude to everybody. No, it doesn't work that way because we have in our mind previous data, which is a distribution, and we're like, okay, this person might be a little more. And so so we use partial pooling shrinkage all the time in real life as well. This is just a way of quantifying the process. We'll take a break in a second here, but so let me just summarize what's on this slide. We can use the distribution of school means to assess the plausibility of any particular school specific estimate. That means, like, we know 15 is weird. The easiest way you can say this is we know school 32 reporting an average of 15 hours is weird. It's like, that's probably not true. So let's see how it's not, but we don't want to just throw the data out. We want to say, like, okay, how can that's nice that these two kids are really studious, but we want to find a way to combine that information. Okay. So we want to use them, but we don't want to take it too literally is one way. We want to take them seriously, but not literally. It's like, it's really great that you have these two kids, one who studies 14 hours, one who studies 16 hours. That's not nothing. That's information. We want to use it, but we don't want to take it super literally. We don't want to assume that the average is actually 15. Okay. So the two high numbers suggest that the school is likely above average, but it's not enough data to fully overcome the prior distribution of school means. So we need much more information to make that conclusion. Okay.